Okay, example 3 here might look a little familiar to you from the last section. It says, often one method is more convenient to use than the other. The following example illustrates a case in which the shell method is preferable. Example 3, find the volume of the solid formed by revolving the region bounded by the graphs of y equals x squared plus 1, that's our upward opening parabola, y equals 0, that's the x-axis, x equals 0 is the y-axis, and x equals 1. And we want to rotate about the x-axis. Now, we did this problem before with the disk method. And let's real quickly just go through that, revisit just to refresh our memory, and then we can compare that to the new shell method and see which is easier. So to do this with the disk method, we're rotating around the y. We want to be perpendicular to the axis of rotation. So this is going to be a two-stage integral. Remember, we want capital R of x squared, upper radius, minus lowercase r of x squared, inner radius. So as we integrate along the y-axis, our first chunk, volume equals, we got to have our pi out front, and the first piece we integrate from 0 to 1, and our upper radius is just the line 1, so capital R of x is 1, and we're going to square it. And then we minus the lowercase r of x, and since we're touching our axis of rotation, that's just a 0. And then to that, we're going to add another integral. And our second integral is where we start to change here, and that's going to be, I forgot my pi out front. We're going to integrate now from 1 to 2, 1 to 2, and our outer radius that touches the top of the rectangle is still 1, 1 squared. And then we're going to minus the inner radius squared. And they gave us our function here, y equals x squared plus 1, y equals x squared plus 1. We want to solve that for x. So minus 1 from each side and square root. So we're going to have y minus 1 square rooted for our inner radius of this second part of the integral. So we're going to have a quantity squared, and that quantity is the root of y minus 1. And we're integrating with respect to y. We need a dy there, and I got to squeeze a dy in right there. So let's clean this up a little bit. We have pi, our integral from 0 to 1. 1 squared is 1, minus 0 squared is 0, so we just get 1 minus 0 is 1, dy, plus pi, integrated from 1 to 2, from 1 to 2, and then we have 1 minus, when we square the square root, that will cancel, and we distribute the negative, so it's going to be negative y plus 1. So that's going to change us to a 2 minus y. And then we're integrating with respect to y dy. So 2 minus y dy. And we're ready to integrate pi. And we integrate 1 with respect to y, and we get y, evaluated from 0 to 1, plus pi. Take the antiderivative with respect to y. It's going to be a 2y minus a half y squared, or y squared over 2. Integrated or evaluated from 1 to 2. And we run our upper and lower limits through there. Let's see, we'll get pi minus 0 plus pi. And then when we work in here, we're going to get 2 times 2 is 4 minus 2. And then subtract our lower limit evaluated, 2 plus a half. Close that off. And when we work all that out, we're going to get pi plus a half pi, which is 3/2 pi. 3/2 pi. You know, not too bad, but it was a double integral, and, you know, we were integrated from 0 to 1 and 1 to 2, so that was a little bit of work. Let's try the same problem with this shell method. So now we're going to do shell method. So look at the picture now. We are wrapping around the y-axis still, but now we're going to be parallel to our axis of rotation. So volume equals 2 pi, integrated from a to b, of p of x times h of x dx. Let's see if this is the easier method. So 2 pi, and we're integrating along the x-axis now. we're perpendicular to the x-axis with our representative rectangle, so our integral from here will be 0 to 1. P of x is our distance from the axis of rotation, and since we are touching our axis of rotation, P of x is just our x-coordinate. And h of x is the height of the rectangle, and the height of the rectangle is given by the function x squared plus 1. And dx. So let's see, distribute that x throughout the parenthesis. We have x to the third plus x dx. And we take the antiderivative, 2 pi. That is going to be x to the fourth over 4 plus x squared over 2 integrated from 0 to 1. So we're going to have 2 pi. Plug in the 1's and we're going to get a fourth plus a half. And then we'd minus 0 plus 0, which just sort of falls right off of there. And a fourth plus a half is 3/4. 2 pi times 3/4. We would get, 6 pi over 4, and that would reduce to 3 pi over 2. Look at that. Same answer, 3 pi over 2. And it looks like the shell method was very preferable to the disk or washer method that we've used in the last section. Lot less work integrating. Right here in example 4, we're going to find the volume of a pontoon. A pontoon is to be made in the shape shown in figure 7.34. The pontoon is designed by rotating the graph of this function, y equals 1 minus 1/16 of x squared, from x values of -4 to +4. We're going to rotate that about the x-axis, where x and y are measured in feet. So here's the pontoon, a 3D representation of it, and then here are the cross sections. So we have to decide, is it going to be easier to do the disk method or the shell method? Well, first let's look at the shell method. Our axis of rotation is the x-axis. So if we are going to use the shell method, our rectangles, our representative elements, will be horizontal to this axis of rotation. And we're going to have to do the right-hand edge here minus this left-hand edge here to get the height, or from this perspective, the length of that rectangle. So if we wanted to do this, we would have to solve this equation for x. Y equals 1 minus x squared over 16. We would have to solve this for x. I would multiply through by a 16 first. Oops, what did I do? That should be y equals 16. Y equals 16 minus x squared. And then I would get the 16 on the other side. 16y minus 16 equals negative x squared. Negative x squared. And then divide through by a negative. X squared equals 16 minus 16y. Square root both sides, and we could factor out the 16 and square root that. So x would equal plus or minus 4 roots of 1 minus y. So here on, back to the picture, the edge of the rectangle over here would be at the edge plus 4 times the root of 1 minus y, and then we would have to subtract the lower or the left-hand piece of that, which is the negative 4 times the root of 1 minus y. So we can see right off the bat, this looks like it's going to turn into a pretty complicated integral. Let's take a look at it from the perspective of the disk method. So the axis of rotation is, of course, the x-axis. If I draw my representative rectangle perpendicular to it now, as opposed to parallel to, and we think about that representative rectangle sliding back and forth, this looks like it might be easier. We have our upper curve will be the function 1 minus 1/16 x squared. Our lower curve would just be the x-axis, or 0. So we have our upper curve minus lower, and that never changes. Pretty simple setup. This problem would be easier to do with the disk method. It is possible with the shell method, but why should we work harder than we have to? Work smarter, not harder. So let's set this up using not the disk or the shell method, but the disk method. So let me move this down here a little bit. So we're going to go back to our old formula, pi, the integral from a to b of capital r of x, our outer radius squared, minus lowercase r of x, our inner radius squared, dx. So let's plug in our problem's numbers. Pi integrated from, on our x-axis, we're going from -4 to +4. Our upper radius is going to be our function, 1 minus x squared over 16 quantity squared. And then our lower radius is 0 since we are touching our axis of rotation. So we could have minus 0 squared, but that is not necessary. So there's our setup. Well, let's see. Before we integrate, we're going to have to FOIL that out. So pi, definite integral from -4 to 4. And if we FOIL this out, we'll have 1 minus x squared over 8 plus x to the 4th over 256 dx. So now we're ready to take the antiderivative. Pi. Let's see, the integral of 1 with respect to x is just x, minus, this is 1/8 x squared, so we raise the power by 1, and now it's x to the 3rd. And we divide by the new power 3, or multiply by 1/3, so that will be x to the 3rd over 24. The next piece, this is 1/256 x to the 4th. Raise the power by 1, x to the 5th, divide by the new power of 5, or multiply by 1/5, and that will turn into a 1280. And we're evaluating that from -4 to 4. Now, I just said a little bit earlier, work smarter, not harder. Can we make that setup any easier? Well, when we look at our cross-section picture here, it looks like we are symmetric about the y-axis. So instead of integrating from -4 all the way to 4, since we are symmetric around that axis, can't we just integrate from 0 to 4 and double it? If we find this area and times it by 2, we'll get the other half there. So instead of working real hard and integrating this from -4 to 4, let's change our lower limit to 0 and just double the area that we find. Put the 2 in front of the pi. And that'll make our work so much easier. If you do go all the way and integrate from -4 to +4, you will get the exact same answer, of course. So we plug in 2 pi. Upper limit goes in, 4 minus 64/24 plus 4 to the 5th power is 1024 over the 1280. And there's our evaluation. We just have to get a common denominator, fix our numerators, work all that, times it by 2 pi, and as a fraction, you'll get 64/15 pi, which is approximately 13.4. And since we were given units, we're talking about the volume of a pontoon. They said that all measurements were given in feet. That would be in feet cubed. So the volume of that pontoon, 8 feet long, would be 13.4 cubic feet. Again, to summarize this example, we had our choice. Would it be easier with the disk method or the shell method? We analyzed from our graph, looked at our axis of rotation, figured out it would be easier with the disk method. Just because the section is on the shell method, we do not have to use the shell method to solve the problem. To use the shell method in example 4, and I did talk about this at the beginning, you would have to solve for x in terms of y in this equation. And we would get that height would be 4 times the root of 1 minus y. Sometimes solving for x can be difficult, or maybe even impossible. In such cases, you must use a vertical rectangle of width delta x, thus making x the variable of integration. The position, horizontal or vertical, of the axis of revolution then determines the method to be used. And this is what we're going to see here in example 5. Now in example 5, they did spoil the surprise. They do write right here after the example, shell method necessary. If they did not give us that clue, maybe we would look at the picture and say, okay, we want to find the volume of this region rotated about Now we're not around the axis, either axis, x or y. Our axis of revolution is the line x equals 2. So we're going to take this area, rotate it around that axis to find the volume. And my first thought would be, hey, maybe we want to do a disk method, or this would be washer actually. And maybe I want my representative element to be perpendicular to this axis of rotation. So we would need to solve this equation, y equals x to the third plus x plus 1. We would want to solve this for x. So let's see, let's move the 1 to the other side. It'll be y minus 1 equals, and then we have x to the third plus x. Anything I can see over here to do would be to factor out an x, then it'd have x squared plus 1 equals y minus 1. It doesn't look like there's any way to solve this equation for x. So we're sort of stuck. We are not going to be able to use the washer method at all. They're forcing us to use the shell method. The shell method is necessary. So let's set up our generic equation. That's going to be 2 pi. And then our integral, p of, in this case it's going to be p of x, h of x, because we are going to integrate with respect to x. You know, we're revolving around our axis of revolution is x is 2, and our representative rectangles are going to be perpendicular to that x-axis, so we will be integrating with respect to x. Now this might be the toughest part here. Up until now, our axis of rotation was always the x-axis or the y-axis. So p of x or p of y was usually just the x-coordinate or the y-coordinate. That is not going to be so in this case. We need to look at the picture, and there, don't want to spoil the surprise. P of x is the distance our representative rectangle is from the axis of revolution. So here's our axis of revolution. If we're right here, how far away are we from the axis of revolution? Well, we're 2 units away. If we are right here, how far away are we from the axis of revolution? We're 1 unit away. So at most, we're going to be 2 units away. And then we're going to move closer and closer by whatever our x-coordinate is. So at any given time, where is our representative rectangle located? Well, at most, it can be 2 units away. And we're going to subtract from that whatever x-coordinate we happen to be on. 2 minus x is our distance from the axis of rotation. What is h of x? H of x is the height of the rectangle. And the height of the rectangle here, we are not touching our x-axis at all. So what we're going to need to do is find the upper curve. This upper curve touches the top of the rectangle, and that is our function, x to the third plus x plus 1. And the bottom of our representative rectangle is hit by this line, y equals 1. So from this, we're going to have to subtract our lower function, or just 1. And then we'll put our dx on the end. So we can simplify this a little bit. The plus 1 minus 1 right here are going to cancel each other out. So the plus 1 and minus 1 are now gone. And we have 2 binomials that we are going to have to FOIL out. So time for a little algebra. 2 pi, and our upper and lower limits, we are integrating along the x-axis. So our lower limit will be 0, our upper limit will be 1. Integral from 0 to 1. And I'm just going to cut to the chase. If we FOIL this out and collect up all our like terms, we're going to wind up with negative x to the fourth plus 2x to the third minus x squared plus 2x dx. So now we have everything ready to rock and roll. Time to find the antiderivative. So we're going to have negative x to the 5th over 5 plus, we'll raise that up to the 4th power, divide by 4, 1/2 x to the 4th. So x to the 4th over 2. The next term, raise the power by 1, divide by the new power, minus x to the 3rd over 3. And then the last one, raise the power up to squared, divide by the new power 2, so we're just going to get plus x squared. And we will evaluate that from 0 to 1. And this shouldn't be too bad to evaluate. Our upper limit is 0. When we do plug in our upper limit is 1, our lower limit is 0. And when we plug that 0 in, every term will just be wiped out. So, plug in the 1 first. Negative a fifth, plus a half, minus a third, plus 1. And just for completeness sakes, if we plug in the 0, we'd have minus a negative 0 plus 0 minus 0 plus 0, which is all meaningless. That goes away. So we work in the brackets, combine up all those fractions, multiply by the 2 pi, and you'll wind up with 29 pi over 15. 29/15 pi. So again, this one, the shell method was necessary. Even if we wanted to, we could not do the disk or washer method. The problem just isn't set up that it would even be possible.